So, oh, the meeting is being recorded, it said, okay.
Yeah, you have a pop-up.
All right. So welcome everybody to the Friday seminar in fluids at Imperial. Today it's a special pleasure to have Unnikrishnan Nair with us as the speaker. Uni and I met about 2 years ago when it was still okay to travel at OSU in Columbus, Ohio. And that's the first time I saw about Uni's work. Very impressive, and I thought it would be great to present that one in the seminar. So in the meantime, Uni is now an assistant professor at FSU, Florida State University in Tallahassee. And he's going to talk today about transition in high-speed flows and its relevance to aero-propulsion systems. So welcome, Uni, and please share your screen, and the floor is yours.
All right. I'm just trying to share the screen here.
Yeah. All righty. And presentation mode. Yep, perfect. Okay.
Yeah. Thank you, Professor Schmidt, for that intro. So I'm Uni. I'm a faculty at FSU. Today's talk will be on transition in high-speed flows and its relevance to aero-propulsion systems. So let me start out by first thanking you guys for the invitation, and it's a great pleasure to share some of our recent research with this community. I would like to acknowledge our collaborators on these projects, Professor Rajan Kumar here at Florida State University, Professor Datta Gaitonde at Ohio State, and our students who have contributed to this work are Nikhil and Ara at FSU. We'd also like to thank continuing support from Office of Naval Research. They have been supporting this research at these institutions, and we of course need lots and lots of computing time, which has been provided by various agencies within the DoD and Ohio Supercomputing Center and the FSU Research Computing Center. So with that, let's talk about some motivational charts here. So why do we need to understand transition to turbulence, especially in high-speed flows? Because whether you think about space applications or military or futuristic civilian transport, high-speed air travel is dependent on reliable prediction of skin friction, heat transfer rates, and reliable predictions of boundary layer performance within internal flow paths. There are a lot of applications where transition to turbulence come into the picture in such systems. I have listed 3 specific examples here because we have been working in these areas over the past few years. The first one is high-speed subsonic jets. As you know, civilian aircrafts as well as military aircrafts can have high subsonic or even supersonic exit jets that throw out a lot of kinetic energy into the ambient, right? So all this shear layer harbor a lot of instabilities in it, and the turbulence that's generated from it can result in aeroacoustic production of noise. And of course, it has very damaging effects on personnel as well as environment. So we need to understand how, from a first principles approach, how come these turbulent eddies or instabilities generate the perceived sound in such turbulent flows in order to control them eventually. The second application I have noted here is the inlet of a supersonic aircraft. Here, issues include things like separation, total pressure loss, mass flow deficits, and again, its impact on engine efficiency and shock trade instability. Because, for example, if you have excessive oscillations in the compression system, you could have unstart, which can damage the aircraft, right? So again, we need to have a very thorough understanding of how boundary layer develops on these compression systems or inlet systems for, again, reliable designs. The final application is hypersonics. The key here is sustained hypersonic flight. If we are to design sustained flight vehicles that are traveling at Mach 6, for example, we need to have a control over where transition may occur, or if it even occurs, can we control it or push it down its location to downstream locations over the aerodynamic surfaces in order to again control the price we pay for enhanced wall loading. So all these applications can be summarized in these few words, right? We need to make our high-speed systems quieter, cheaper, faster, and safer. So that is why we do what we do, right? So with that, let's go into the technical component of the talk. Before I present some results, some brief introduction on the tools that we are using to do this. Ours is a primarily a computational analysis group where we rely on high fidelity simulations to probe these flow systems. Typically, we use two-dimensional or three-dimensional simulations of unsteady compressible Navier-Stokes equations. These are solvers on which implements the strong conservation form on curvilinear coordinates so that we can handle some complex geometries. The in-house code has high order capabilities and variants like LES, RANDs, stability tools, and the FT suite, which is essentially a specific class of model decompositions that can handle compressible flows. In order to give some additional details, temporal schemes include RK3 or beam warming type schemes. For spatial resolution, we use wherever we have smooth flow fields, the solver adopts like a high order compact scheme and Poitier filter approach. If you have enhanced compressibility and shocks, for example, this is a highly overexpanded jet. It's a heated jet with shock cells and a highly asymmetric acoustic near field. You can see it's not a circular jet, right? In such scenarios, we can use Riemann solvers or a hybrid approach which combines both these. So these are some basic information on our tool that the tools that are going to be used in this analysis. So going ahead, as we discussed in the abstract, we have three components in today's seminar. We'll first start with hypersonics, and what we are going to address there is the effect of wall thermal conditions on a very key instability mode in hypersonic boundary layers. As you cool the wall, for example, that qualitative nature of instability response in the boundary layer changes, and that's what we are going to quantify today. And we will look at some nonlinear stages in that instability evolution. And the second part transitions into a talk about an operator-free method, which can be used to study secondary instabilities in such non-linearly distorted flow fields, which is a matrix-free or an operator-free method that can be easily implemented in existing Navier-Stokes solvers. And we will look at certain secondary instability characteristics of macmode instability. Finally, we will conclude with an application of the stability tools and transition analysis in an aero-propulsion problem. Specifically, again, we will look at a supersonic inlet and see how we can get more physics into this complex flow field by adopting a very fundamental stability-based analysis. So with that, let's go into the first section. So if you look at the literature, there's this famous diagram from Mokovin. Transition in high-speed boundary layers, for example, can progress through various different pathways depending on free stream conditions. It starts with receptivity, and it could follow the linear eigenmode growth or a non-model or algebraic growth, eventually reaching nonlinear saturation and breakdown. Sometimes if the free stream conditions are high intensity, sometimes you could also get this bypass mechanism, which circumvents all this model growth. At the end of the day, you get some sort of a saturated flow, and then it breaks down into turbulence. In order to focus on hypersonic boundary layers, that's a topic we are going to discuss today. Let's bring this very basic diagram. What I'm showing here is a flat plate with the leading edge facing a uniform free stream. If you look at the theoretical incompressible limit or a Blaschius profile, you know that you have this classic neutral curve or the thumb curve, which is corresponding to the Tolman-Schlichting instability. Let's say we are tracking a constant frequency wave in the downstream direction. It has this finite streamwise span where it is going to undergo linear amplification, and it's going to damp out outside that region. The issue is once you reach Mach 4, Mach 5, this neutral curve starts bifurcating. That means you have, like, it splits out into, say, two different patches. Now the problem is, even if the boundary layer survives this linear growth, if you look at the growth rates of the second curve, it's an order of magnitude higher than what it experienced in the first curve. So the second curve is literally called the second mode or the Mach mode. Mach mode has a higher growth rate, and hence, of course, it has a higher chance to reach that critical amplitude to trip the boundary layer. theoretical analysis have shown that you can have many such curves which appear in the downstream directions in high-speed boundary layers, which corresponds to implicit instabilities of the mean flow. So this is the mode we are going to focus today, the mode, or the so-called Mach mode. One of the biggest challenges when we study high-speed transition is the sheer parametric range of scenarios that can come into play. For example, Mach mode instability is very sensitive to free stream conditions, both the mean flow parameters as well as the disturbance condition. It can also be highly dependent on surface properties of the vehicle, geometrical features. For example, if we have catalytic surfaces or non-equilibrium aerothermochemistry in the flow, all these parameters can qualitatively change how that mode evolves in the flow. And one big factor is wall thermal conditions. That's our topic for today. When I say wall thermal conditions, what I mean is Mach mode in the boundary layer can evolve whether depending on whether it is an adiabatic wall, a hot wall, or a cold wall. And cold wall is going to be, again, the focus of the discussion here. The first basic observation is linear stability has shown that if you cool the wall, the Mach mode destabilizes, whereas the first mode shows a reduction in its growth rate. So what I'm showing here is the complex part of the frequency omega I. That's the growth rate. This is a simple 1D LST or linear stability analysis. The red curve is a diabatic wall and the blue one is a cold wall. As you can see, the growth rates have amplified when you cool the wall and the wavelengths have decreased. So the frequency, the length scales shrink and amplification rate increases. That's what typically happens when you cool the wall. So why do we even need to study cold wall trends in hypersonic boundary layers? This is because when you think about ground test, where high enthalpy tunnels are used for short duration runs, the thermal inertia of the body may not actually allow it to heat up or warm up to that recovery temperature or adiabatic temperature, which is more likely the scenario in an actual flight. So it's important to reconcile the differences between such cold wall conditions versus an in-flight condition in order to draw reliable insights or high fidelity insights from our elaborate experiments and computations. So that's why such cold wall simulations are very important and practical for hypersonic studies. So this is the problem setup we are going to address. We have a Mach 6 boundary layer. It's a free stream condition. We assume it's an ideal gas, and the adiabatic temperature is very close to 7. So when you see 7, you should understand that we are talking about a near adiabatic wall. And this is a test matrix here. So what we are going to do is we are going to systematically reduce the wall temperature from the near adiabatic condition all the way till a very cold condition. And 1D LST is basically one-dimensional analysis. It will tell us what are the qualitative changes that we can expect in the instability mode. So this is the first level of probing we are going to use in order to categorize what instabilities can occur in a boundary layer as we cool it. The next phase includes two-dimensional DNS, where we are going to probe into the spatial structure of these instabilities in greater detail. And finally, we do 3D DNS for select cases because of course it's expensive, but it also gives us insights into possible transition, nonlinear scenarios, and also three-dimensional effects are more commonly seen in realistic experiments or flight simulations where you have wave packet forcing in the boundary layer. So these are the different tools we are going to use for our study. So before even talking about the instabilities, look at what happens to the mean flow when you cool the wall. What I'm showing here is the streamwise velocity, that's the wall normal profile, U, and this is a temperature, that's a temperature profile, and this is the function which gives us the generalized inflection point. So that will be something like d by dy of rho times du by dy. So you can see there is an inflection point for the adiabatic wall condition. As we cool the wall, this is a cooler temperature, T wall phi, you can see the hydrodynamic and thermal boundary layer, they are becoming thinner. So another observation is you get, instead of one generalized inflection point, you get two. And as we keep cooling the wall, the boundary layer is thinning out. It's getting more fuller in a way. And the GIPs cancel off, and you no longer have a GIP in the mean flow, but that doesn't mean it is lacking in viscid instability. You can still show using Rayleigh equation that there is something called as this relative supersonic region where U minus C by A is greater than 1, U being the velocity of the flow, C being the phase speed of the instability, and A is the sonic speed. So this always exists near the wall. So it's always implicitly unstable, this profile, but you have a lot of qualitative differences in the length scales in the boundary layer as you cool the wall. And let's now look at the instability mechanism using 1D LST. If you look at hypersonic literature, it's very common to see this phase speed plot where you show the trajectory of the unstable mode with respect to the real and imaginary component of the phase speed. This is basically the amplification rate. These three lines indicate three critical speed limits in the flow. This is this is something like the slow acoustic wave, which moves at U minus C. This is those waves that travel or convect in the flow, like vertical or entropic, that is U. And this is a fast acoustic wave, U plus C. The mode that originates from this speed limit is known as mode S because it came from the slow acoustic speed limit. And mode S seems to be the most aggressive second mode instability in adiabatic walls. This is well documented in literature. But the interesting thing is, as we keep cooling the wall, the instability shifts to the other end of the phase speed spectrum. Mode S gets destabilized. Mode F, that is a mode which starts from this limit, becomes unstable in a specific region, which is a second mode neutral curve. And that's the bad guy here. So, but the most interesting thing we are looking for in this analysis is what happens to this wave as we cool the wall further. So this is T-wall 0.5. You can see that the range of instability is pushing closer to that slow wave speed limit as this trajectory shows. And at extreme cooling, what happens is it cuts across that limit. And if you closely look at the Eigen mode, which emerges from that U minus C limit, there is a second zone of instability here. So in literature, this is known as a supersonic mode because it is traveling at a phase speed less than the slow acoustic wave. That's less than U minus A. And when you have a near stable or an unstable wave at very low phase speeds like this, it leads to radiation from the boundary layer. So physically what happens is that if you just keep transmitting waves to the boundary layer and keep cooling the surface, at some threshold, you are going to see emissions from or radiation coming out of the boundary layer because of this wave speed limit. So that is interesting physics we are going to look at here. So of course, the wave speed limit is also associated with a qualitative change in the eigenfunction itself. So what I'm going to show here is how does that eigenfunction, this is all from simple 1D LST, okay? So how does eigenfunction of the instability change prior to that crossover and immediately after that crossover? So this shows the vorticity and acoustic component in the instability just before it intersects that wave limit. So it's as expected. You have a very nice compact wall normal support to that instability wave. But the moment it crosses over into the slower wave phase speed limits, it suddenly changes its character. What comes out of that limit there is a highly oscillatory function. That means it's no longer compact and it's going to throw out energy from the boundary layer into the free stream. That is some nice observation we have using simple 1D LST. And an important observation here is it is not just sound waves that come out of the eigenfunction. It's actually even throwing out vorticity into the free stream. So it is radiating out acoustic energy and vertical energy into the free stream from the hypersonic boundary layer. So we went ahead and then did a two-dimensional DNS to get more closer insight in, or more detailed insight into the internal structure of these instabilities. What I'm showing here is the internal structure of macmode. This is what is known as a dipole structure. That's because this is something like total internal reflection optical fibers, if you will. So you can see that there's a zero flux lane across which there is no energy being transferred between the boundary layer and the outside. So if you cool the wall, what happens is this trap structure ruptures and you get this continuous flux lines between the boundary layer and the free stream. So you see the trap nature of macmode is ruptured and it goes into this radiating mode. As you change the wall temperature, it's consistently predicted in DNS as well as LST. People who do research in hypersonic transition, the first question they ask is, well, we have a mechanism that naturally throw out energy from the boundary layer. Can we use it to mitigate transition? So the question is, if we can say that if we cool the wall, the boundary layer is going to throw out energy, can we use it to control transition? Well, it's an option worth pursuing, right? So the first step is to quantify that energy. What's coming out of the boundary layer as we cool it? So this is basically an energy flux integrated at a given wall normal distance in the flow, in the domain. Outside the boundary layer, you can see that as we cool the wall, these are different wall temperatures. It monotonically increases. There is an around 8th order of magnitude increase in the energy flux coming out of the boundary layer as we cool the wall. So good. So now the question is, what does it imply for wall pressure fluctuations? If it is really helpful, it should probably attenuate wall pressure perturbations, right? So when we look at the wall pressure perturbations, unfortunately, we cannot recreate an inverse trend in the pressure perturbations, because as we cool the wall, the competing mechanisms are second mode destabilization and second mode radiation. The radiation is not sufficient enough to throw out enough energy from the boundary layer to attenuate or kill that instability. So this is the RMS for different wall temperatures. So it's not very promising, at least from these 2D simulations. Now what we are going to do is let's do a more realistic 3-dimensional DNS. Here, what I'm going to show is first we design a wave packet forcing, which is centered around the most amplified second mode instability depending on our simulation domain. So you put in the wave parameters like frequencies and wave numbers that really captures that wave which transits through that neutral curve. And we are going to predict, we are going to compute its evolution through the hypersonic boundary layer. So what I'm showing here is two scenarios, that is T-wall 7, the adiabatic case, and T-wall 0.5, extremely cooled case. This is the eventual state of the wave packet at the end of the computation towards the exit. You can see that in the near adiabatic wall, the wave is actually attenuating. We had to really blow up that Q criterion ISO level to bring up that structure. And it is retaining its 2D structure because second mode instability is inherently a 2-dimensional instability, and it's attenuating. But when we cool the wall, even though there is a loss of energy through radiation, we get a highly virulent turbulent spot by the end of the simulation. You get this nice coherent, hairpin structures and a highly turbulized spot in the boundary layer. So even a visual inspection tells us that this is going to trip the boundary layer. In order to give a more realistic visualization of what happens in the cold wall, this movie shows how the second mode wave packet radiates out energy into the free stream as it propagates to the boundary layer. But you can see inside the boundary layer, it's still tripping the mean flow. So it's not helpful, at least in these simulations. We cannot depend on that radiation mechanism as a transition control technique, at least under the given circumstances. So now what we are going to do is, well, we couldn't control it, but at least can we quantify what is happening under cold wall scenarios. So this movie shows you how T-wall 3, 1.3, and 0.1, these are the cooler cases. As you see, the more we cool the wall, the more virulent that turbulent spot is becoming, right? So the moderately cooled wall has this turbulent spot bifurcating into a leading turbulent head and a trailing harmonic, as you can see in this first movie. But as we decrease the wall temperature, the boundary layer is becoming more susceptible to transition. Non-linearity is amplified. The wave packet become more dispersed and stretched out. And you get this extremely turbulent spot by the end of the simulation. And these are intermittent spurts of turbulence that happen in the wake of the head region. So there is a lot of qualitative changes that happens in the wave packet propagation depending on the wall thermal conditions. And we need to keep in mind the qualitative differences when we interpolate our low speed experiments or computations and try to make predictions for a real life flight scenario. So for a designer, the question is, what impact do I have on wall loading characteristics, right? So that's what an aerodynamicist should be interested in naturally. So for that, we are going to take a closer look at the turbulent spot structure itself. This is a top view of the hot and the cold wall turbulent spots that is generated during the simulation. Of course, there are obvious differences between these. For example, in the hotter wall, we have a much more broader spots as opposed to slender and finer scale structures in the cold wall case. If you look at the spreading angle, it's not very sensitive to wall thermal conditions. That's because we found the spreading angle to be dictated by the boundary layer edge condition. And it matches what experimentalists have found. Around 4 degrees is what comes out for a Mach 6 boundary layer. Another interesting thing is, can we explain the spreading mechanism in the lateral direction, because it's also important to quantify how these spots spread in the transverse direction, right? So this is a streamwise, and this is, say, the lateral dimension or the spanwise dimension. For that, there was an earlier study by Redford et al. Who looked at the so-called lateral jet mechanism. To analyze that theory, we extracted the leading energetic mode in the wave packet as it exits the domain. So this is a streamwise plane. I'm showing this is a wall normal coordinate. This is the spanwise coordinate. This is being recorded at the exit. This is the leading POD mode of the spanwise velocity W, which is in this direction. You can see that if you look at the edge of the boundary layer, or the edge of the turbulence spot, you have this nice coherent structure that is pumping out material from within the center to the lateral edges. So that is known as the upwash of fluid through the lateral jet mechanism. You also have some couple of streamwise vortices sandwiched between those structures. So what happens is this mechanism can explain why the spot has a tendency to spread in the transverse direction compared to its propagation direction. On the other hand, if you look at the cool wall, the leading energetic mode doesn't have any sort of coherence in it because of the more aggressive breakup and dispersive nature of that wave packet. Such mechanisms are weakened, and that could be one way to explain why this spot is more elongated rather than broad in the cooler wall. And of course, the final component of interest to, again, designers would be wall loading, right? So for that, we are looking at skin friction and heat transfer characteristics. This is the near wall velocity, streamwise velocity underneath that wave packet in the moderately cooled and the highly cooled case. This is a surrogate for skin friction. And you can see that the high intensity skin friction effects are limited to the head region in warmer walls, whereas the highly cooled wall has extremely high skin friction impact in the trailing edge of the wave packet, because you have this intermittent spurt of turbulent spots coming, or turbulent activity that is being generated even after the head passes the domain, right? So these streaks can record very high localized patches of skin friction on the vertical surface, for example. If you record the peak value at the exit, this is time, and that is peak value of CF. You see the red curve is the adiabatic, the T wall 3, which is the warmer wall, or relatively warmer wall. There is one small hump that is caused due to this head. But if you look at the cooler walls, you have a much sustained levels of higher skin friction being induced on the surface because of this structure. And it's almost twice as that of the T wall 3 case for much cooler wall. So it's a very high impact on wall loading. Similar story for the heat transfer. This is the heat transfer coefficient on the surface for T wall 3, T wall 0.5 and 0.1. You are looking at the skin friction distribution on a line like this in time. So this is Z, and that's time. You can see that for the relatively warmer wall, you have moderate impact in terms of heat transfer, but you get much elongated sustained zones of high intensity heat transfer for the extremely cooled walls. And they primarily exist in the trailing part of those wave packets. So this really shows us nonlinear regions of these wave packets are very important to quantify if we are to accurately estimate the wall loading on these surfaces. So that's where we transition into the next phase of our talk that looks at the nonlinear part of transition. These are several different calculations just to show that in all the cases, for example, like the first mode induced transition or the second mode or a wave packet induced transition, or even a multi-mode transition, multi-frequency component induced transition, we have the peak wall loading, as you know, after the primary wave saturates, and nonlinearities tend to dominate the flow, causing this intermodal interactions. So the question is, in order to have very quick, computationally inexpensive predictions for those later stages of transition, we really need to mature our linear stability tools to handle those flow fields. And that's why secondary instability study is quite important from a practical view, for example. Because when we mature our primary stability tools in order to accommodate for that nonlinearly distorted flow, we can have quick estimates of where could transition happen for a given geometry, what are the spectrum involved. For example, what are the wave number frequency combinations of the modes that drive transition in an actual scenario. And even if you think about a globally unstable flow like cavities or wakes or even large SBLI bubbles, what happens is that after that critical Reynolds number where you have this oscillatory state, primary eigenfunctions may not necessarily actually capture what scales are dominant in that flow. For that, we really need to get a sort of that secondary instability modes in these complex three-dimensional flows, for example. So that's why we need to have some generalized framework to perform secondary instability in three-dimensional flows. And in this talk, we will look at a generalized tool to do secondary instability, specifically applied for the second mode instability in hypersonic boundary layers. So before we even talk about secondary instability, let's first characterize the primary instability of the wave we are talking about. So this is a Mach 6 boundary layer, flat plate boundary layer, in which we have an actuation which puts in a monochromatic wave, and naturally it undergoes amplification, linear amplification in that second neutral curve. And if you look at closely that zone of amplification, you see this classic dual lobe structure to the second mode instability. And if you look at the density perturbations, this is very similar to what experimentalists show in shadow graphs, for example. You have this rock-shaped pattern that emerges when second mode is appearing in high-speed boundary layers under these conditions. Now let's see what happens when you have the nonlinear scenario. When we have the nonlinearities picking up in the flow, the structure slightly changes. You no longer have a symmetric distribution. That's the first observation, right? You have this distorted wave pattern and this N-wave structure to it. That's because this primary is being superimposed with its harmonic. So that's causing this asymmetric pattern in the combined response. And if you look at the density perturbations, you have, again, an asymmetric, highly interwoven type of rock-shaped structures in this nonlinear wave. So there are some nuances in how the shadow graph looks like, for example, if it is a linear wave versus it's a nonlinear wave. So the question is, what is different in these responses? Let's look at the wall pressure perturbations. The red one here shows the linear P prime on the wall. It's normalized by its respective peak amplitude. And the green one is the nonlinear scenario. You can see this is quite symmetric, the red curve, and the green one is slightly shifted because the mean flow is no longer of a laminar function, right? It has nonlinear distortion, so the mean flow itself is changing. And of course, it is asymmetric. But the more interesting feature we will explore here is this trailing part. As the primary envelope closes, you have a second zone of amplification coming in the nonlinear scenario. If you do a model decomposition on the nonlinear response, you can cleanly split it out into the primary wave at omega naught, which, for example, is our forcing frequency, and its superharmonic. And if there are higher, it will come up in the following modes. But the important thing to note here is that second zone of amplification is actually driven primarily by the fundamental itself. So we have that second zone of support here corresponding to that. Why is that important? Because when we actually did the DNS on this flow, we saw that that trailing part is what really drives transition. That's where non-parallel effects are very strong. You have a lot of oblique modes developing in it. So we really want to know the secondary instability characteristics of that zone in order to quantify transition. So that's the motivation to study this problem. So the question is, how do we study that secondary instability characteristics? We know that our laminar eigenfunctions, the laminar mean, the basic state, for example, this is a corresponding GNS, the laminar flow field, is sufficient enough to study our primary instability characteristics. But when we go to the saturated flow, we need to account for that periodic oscillations maybe in space as well as time. And that's where people have done a lot of work on flow K-type analysis for fluid systems, right? So this shows the spatial distribution in the distorted U, V, and pressure and density variables in the hypersonic boundary layer. And these are the respective oscillations in time. So it's a spatio-temporally distorted flow. How do we do the secondary instability or flow K-type analysis without depending on the operator itself? That's the key question here. So let's first determine or define this flow to be a spatio-temporally varying quantity. That's Q is some general variable of the flow, which varies in space and time. So that has a time invariant function that is just the basic state which stays forever. And now we can also split it into a fluctuating component, which is time dependent. And we explicitly mentioned that that is a T periodic function. So that is the distorted quantity. Now, if we linearize the govern equations implicitly, how do we do that? By imposing a body force. But that body force is defined as basically this is a time derivative in Navier-Stokes, and that is a spatial operator. So if we extract this body force from the Navier-Stokes solver, we can use it to implicitly linearize it or arrest the basic state at any given condition. And then we can explore the linear tendencies of that flow. And it boils down to this linearized equation where you have the perturbation quantities and the Jacobian. This Jacobian is time invariant or constant if you are talking about this laminar case where it is primary instability, and it is a function of the basic state and will become unsteady when it is a t-periodic state or when we are talking about secondary instability. This is also somewhat similar to the work by Tuber and Sundam in 2009, where they did some implicit linearization for SBLI unsteadiness, evaluating linear tendencies in SBLI unsteadiness. So this is the framework we are going to use for secondary instability analysis. The best part of this approach is it helps us to tweak the existing Navier-Stokes solvers we use on a daily basis for our computations with very minimal modifications and get this very versatile secondary instability tool. The other advantages are it also helps us to transfer all the high order formulations we use in our Navier-Stokes solver to the perturbation analysis too. And of course, it allows us to leverage the compressible 3D formulation without any limitations on the geometrical complexity of the flow field. Also, if your solver has capabilities to do things like source terms for chemistry or additional equations for vibration non-equilibrium, all these things can be implicitly linearized into this new system. So that's a convenient property that comes along with this tool. So let's look at what comes of this analysis. So what I'm showing here first is the linear response for the basic state and the linear response for the periodic state. So this is the perturbation spectrum. This is the streamwise distance. That's the span-wise wave number, Kz. This is the MFP result. MFP stands for mean flow perturbation. That means you are extracting the linear perturbations around the time-independent mean flow. Nothing too exciting there. It's a monotonic variation. But this is the linear response of the unsteady flow perturbation, UFP. Unsteady flow perturbation because you are extracting the linear tendencies about an unsteady flow. In this case, it is a time periodic flow, but in general, it can be any unsteady flow. The first observation, at this point, I will only tell that it's a highly non-trivial distribution of energy in this wave number spectrum. We will come back to this figure later in the context of a DNS, but as you can see, there's a lot more information that comes out from a UFP spectrum as opposed to our MFP spectrum. And we will use this to reconcile some of our observations of what we see in DNS. And why do we have a patch over there? That's because that is the region which most aggressively amplify oblique modes. And that is the region where the primary envelope ends and that secondary envelope picks up in our distorted mean flow. So in order to really understand how good or bad that UFP prediction was, we really need to do a benchmark simulation. Here, we consider DNS as a truth model. This DNS basically uses a blowing suction strip to put in that second mode wave, and it undergoes linear amplification, nonlinear saturation, and eventual tripping into a fully turbulent boundary layer. If you zoom in onto that region, this movie will show you what's happening. That circled region there corresponds to the second envelope in our wall pressure perturbations. You can see there are, until that location, the second mode is rollers, basically. These are the 2D waves. But immediately those oblique modes start coming up. They create this lambda vortices, and eventually you get a forest of hairpins, right? That's how turbulence seems to originate in these flat plate configurations. And this undergoes what is known as a fundamental resonance mechanism, because these oblique modes are also at that fundamental frequency. So, well, this is what the DNS tells us is going to happen. In this figure, what we are going to do is we will compare our UFP prediction. This is the wave number space. This is frequency space. This is coming from the UFP. We are going to compare it to the DNS prediction. So this is the wave number spectrum that comes from the DNS. You can see that quantitatively and qualitatively, it actually captures a lot of features that comes in the DNS. UFP is good enough to capture, for example, say that dual lobe nature where real amplification of oblique modes take place, the actual wave number at which it's happening, and also qualitative nature of spectral distribution of energy till the breakdown phase. So it really pushes the envelope of linear stability capabilities into this later stages of transition without actually forming the operator using all the cumbersome manipulations. Also, we can look at this frequency spectra between UFP and DNS. If you want a more quantitative evaluation, we can look at energy. Because this is linear, absolute magnitude doesn't make any sense. So what we do is we normalize the energy content with respect to the fundamental. You can see there is a real reasonably good estimate of energy cascade in those frequencies. We can always fine tune the UFP calculation. This was the first cut or a blind simulation. The real power of this chart is the DNS spectrum here takes what, a week at least of calculation on supercomputers, because it's a highly resolved several hundreds of million point calculation, whereas UFP takes a few hours on a workstation. So if you really need to explore nonlinear states of transition using a computationally inexpensive tool, UFP seems to be promising, at least in the cases we have explored thus far. So that is, we think this is a very promising way to go ahead for probing nonlinear states of hypersonic transition. So with that, we will go on to the last phase of our talk today. How does this transition prediction tools or linear stability tools really help us in applied problems like aero-propulsion? What I'm showing here is something we have been researching at FSU for the last 2 years. This is a so-called mixed compression inlet. This is at Mark 3. So such inlets can be commonly found in high-speed projectiles or high-speed aircrafts. This is typically called as a chin inlet. What happens here is part of the compression happens outside on the ramp, and part of the compression occurs inside the isolator through this oblique shock train. So the idea is, how can we design the system to be robust enough so that the shock train is not thrown off the isolator when we have perturbations coming from behind, or when we have uncertainty coming in, unaccounted disturbances coming from the free stream. Because if this shock train is destabilized, we get unstart phenomena, right? So this is a collaborative effort between Florida State University, Air Force Research Laboratory at Eigen, which is a couple of hours drive from here, and the Defense Science and Technology Laboratory, UK. At FSU, the computational aspect has 3 focus areas, and that's going to be the discussion item in the remaining of the seminar. So the first aspect looks at low fidelity CFD like RANs, because it's a very important design tool. The idea there is to calibrate some of these models with experimental counterparts. We have experiments also going on at FSU here. So the idea is, if we can calibrate our low fidelity CFD models, we can always look at design iterations, parametric efficiency parameters like mass flow deficits or total pressure losses, and shock train distribution when we have slight modifications in geometry. So that is a very production type tool that is quite useful for design iterations. The second aspect of our analysis in CFD is more fundamental, where we look at component-wise details of this flow and try to understand the dynamics involved in the boundary layer processes that is going into the inlet, and what's happening within the shock boundary layer interactions. The third component is, I would say, it's more high fidelity CFD as truth model. So there we are trying to do as much as possible the whole domain. In either we might have to go for wall modeled or maybe wall resolved in very special cases, but the idea is to get the whole system simulated using high fidelity CFD. In this talk, I'll be focusing on the fundamental aspect of this analysis, because it matches quite a bit with what we have already covered for transition to turbulence in high-speed flows. So the first part of this analysis will look at the external ramp. We will see what's happening over the ramp and try to understand its dynamics before moving on to the SBLI near the cow. So what I'm showing here is it's a 2-dimensional mean flow, right? Because it's span-wise periodic assumption. So this shows the mean streamwise velocity, and there is a separation over the ramp. This is a top view of that velocity distribution. You have the separation and reattachment regions. The first step is, of course, to get some estimates of linear tendencies in this flow. The easiest way is to put in a linear pulse, run our implicitly linearized solver to get those modes. Of course, there are going to be shear layer modes supported in this edge. So that pulse propagates downstream, and you can see some high span-wise coherent 2-dimensional type modes coming off because of the convective instabilities. And if you look at the pressure spectrum, you get this thumb curve sort of region, but it neatly coincides into that narrow spectrum over there at Stahel number 1.8. 1.8 because it's being normalized by the height of the channel. But that band there is really the KH type instabilities that is supported within the shear layer. It's convective in nature, and it primarily comes out in our two-dimensional analysis. But another interesting aspect of this region is if we keep playing that movie for long enough, all the convective instabilities move out of the domain, and then we get this nice standing wave, which has a very specific span-wise wave number, as you can see in this movie. And it's also stationary. You don't see it oscillating. It just stays there and grows monotonically with a positive growth rate. So we looked at the Gottler number for this curved wall, and it's well above the threshold for instability criteria. So this could very well be Gottler instability vortices. And they are streamwise vortices, and they have a absolute instability character to it, unlike those KH structures. So the idea is, how do we extract these modes and classify them as stability modes, right? Because that's what we are looking for, to explain fundamental flow phenomena by extracting the building blocks of the dynamics. So for that, remember we have this UFP tool. It is implicitly linearized. If we assume our basic state is invariant in time, it reverts to the primary instability analysis, and it gives us a linearized perturbation. All we have to do is pass it through a Krylov subspace iteration like Arnoldi. So you get this orthonormalized subspace vectors, and you get the smaller Heisenberg metrics. And if we can get the Ritz value, as done in the time stepper approach, we estimate the leading eigenmodes of the basic state. And this is a well-known time stepper approach, but we are coupling that process to the implicitly linearized Navier-Stokes solver in this scenario. So let's see what are the stability modes we are getting. The two-dimensional analysis picks up a Straw number at around 1.8, which corresponds to that thin band, which I showed in the previous slide. That is our shear layer mode, which originates, we can see the spatial support starts out in the edge of the bubble, and it just convex downstream. And if you can see, this is a negative growth rate, minus 0.1, as expected of a convective instability. Further analysis, three-dimensional analysis of the flow picks up this mode, which is Straw number 0. That means it's a stationary mode, and as a positive growth rate, that means it's sort of an absolute instability. It's monotonically growing in time. That is a stationary mode, and it has this straw-like structure on the curved wall. That is a Gottler type vortices. You have this multi-layer or deck-like structure within the bubble. So this patch here, the shaded patch, is the bubble. So it's a 3D mode, and it's going to amplify in the linear sense. So the question is, how does a real life scenario look like? These are linear estimates, right? So for that, we did the LES of the ramp. What we do here is we remove the top part, the cowl, and just simulate the wall using a digital filter that puts in perturbations at a given length scale and frequency scale. The LES actually captures these roller structures. If you can closely look at the bubble, those roller structures are reminiscent of our shear layer modes. And it also has a streamwise elongated vortices, which closely represent the wave number and wave number distribution in the stationary mode. In the real or the realistic LES scenario, what happens is the shear layer modes drive the secondary instabilities on the stationary modes, leading to these hairpin vortices. And the hairpin vortices trip the boundary layer. By the time it reaches the ramp isolator junction, right here, we have a highly turbulized boundary layer. And there is this nice paper by Lee and Malik in 1995. They saw that when we have stationary Gottler type vortices, the so-called even or varicose modes actually looks like these hairpins. So they are actual secondary instabilities of this stationary mode. They did this using nonlinear PSE. Another thing is, how good is our linear estimate of spectrum, not just eigenfunctions. You can also analyze the spectrum by doing an FFT, for example. This is a linear estimate, that is a LES. You can see that there is the red patch show you how big the bubble is. Of course, it's going to be different in the LES because of all the transition and unsteadiness in it. You can see if you scale these frequencies by the length of the bubble, this has a better match. So that means by using a computationally inexpensive tool, we get a decent estimate of this dynamics. Finally, we this is my second last chart. So what we do here is we just completed some dynamic analysis of external flow. We will look at the internal flow right at the junction there. Why is that junction important? Because that's housing the most important SBLI in this flow, one of the most important SBLI, because if this cowl SBLI is sensitive to perturbations, it can destabilize the entire terrain. So the idea is, can we design this junction using some specific geometry so that you create a more stable basin for that SBLI over there, and it act as a passive control strategy, right? So we tested a few design iterations, Two such designs are a step and a notch. So this is a step geometry, which is also candidate geometry for that junction. This is a notch. The first step here too is linear estimation. That's basically looking at the linear spectrum of these perturbations. This is streamwise distance, that is frequency. What we see here is there are three bands of frequency distributions in it, if you will. One is a really low frequency component, a medium, and a high. The low frequency component more looks like a vague mode associated with step flows, for example, that scales with, say, the bubble, the global scale of the bubble. Then you have this patch, which has a long downstream extent, that is basically the converting or the shear layer modes here. And you have a higher frequency mode, which could be the those finer scales limited to the leading part of the step. The important thing is when we compare the spectra of the notch with the step, we see that that low frequency component is totally avoided in this case because we have a much smaller recirculation bubble. We prevent that from happening in this this geometry. Another observation here is the mean flow itself is very robust to the incoming boundary layer thickness. The step flow is highly sensitive to what the boundary layer is, what boundary layer we are imposing upstream, whereas this seems to be more robust to it. So the linear analysis tells us that the notch has several desirable features we are looking for in this candidate geometry. Finally, we are currently looking at a realistic scenario of that junction design. This is the LES of the ramp and the cowl, putting the shock reflection at the cowl, you get the first SBLI over here. This is a benchmark case where you can see the junction is a straight line, that's a facet. This is a very rich flow. It has several mechanisms in it. For example, separation, transition, SBLI, acoustic emissions, a whole lot of physics going on simultaneously, right? If you look at the mean flow, you can see there is this impinging shock. You have the reflected shock coming in and then bifurcating into two parts, one emanating at the region where the boundary layer is peeling off, the other component coming out at right where that impingement is, and then you have the reattachment zone resulting in compression waves, creating this third shock wave. If you look at the frequency bands, again, you see that high frequency, medium, and low frequency, quite well established in two-dimensional SBLI literature, which says that low frequency is the bubble oscillation or the breathing frequency, and also associated with the low frequency perturbations in the shock wave. And we have the middle band, which really picks up after the interaction because of shear layer instabilities. And the highest band here corresponds to frequencies that are present in the boundary layer in a universal sense, even before the interaction begins. So right now we are analyzing this notch geometry. If you can see this, it's slightly different. You have the notch design there. It seems to get rid of that low frequency peak in a reasonable manner, but we are still exploring the advantages or nuances associated with that particular design feature. So this is how we reconcile linear estimations with more complex LES, and we can leverage our simple tools to give us design suggestions for this complex flow paths encountered in aero-propulsion systems. This is work ongoing. So with that, I would conclude. We discussed hypersonics, how thermal sensitivity or second mode can result in totally different types of wave packet evolution. Cooling really does not seem to mitigate transition. It's only making it worse. And we talked about superharmonic structures in second mode instability and how we can use a matrix-free technique to extract nonlinear linear tendencies of the saturated flow that comes in the nonlinear stages of transition. Finally, we applied those stability tools to supersonic inlet, which is an aero-propulsion problem, and identified some key features that drive transition on the ramp and unsteadiness associated with the call SBLI. With that, I would like to thank you guys for this opportunity, and feel free to check out our website if you're interested in this work. Thank you.
All right. Thank you very much, Uni. Very interesting talk. The floor is open for questions from the audience. If you have some, maybe you think about it. In the meantime, let me ask you one.
Yeah.
For your UFP method, it's how do you enforce or ensure that there is enough timescale separation between a evolution of the base flow or a primary instability and a secondary instability? If they're too close, then you mingle the two up, right? So there must be something that needs to be ensured before you can actually make conclusions about a secondary instability.
Yeah, so I think in terms of the scales, we are, for example, if this is a numerical procedure, right? So the integration time is driven by, say, the CFL, for example, and we are doing it at a much, when the CFD numerical limitation, I think, is much severe than the primary scales of unsteadiness in it. So the procedure is proceeding at the time scales of the stability criteria of the solver. So that should tell us that the procedure itself is not being contaminated. But as you said, there should be checks. Are we getting what we are seeing, what we should show, or what we should see? So for that, we put in some known frequencies in the flow. For, say, example, if we are looking at omega as the base flow disturbance, we can put in we put in omega, and we shouldn't see 2 omega coming out, because that means it's a true nonlinear interaction. We can see omega, then 3 omega, 5 omega. So we can put in known frequencies and make sure we are not seeing that something we shouldn't see. So those are some things we have tried out to make sure we are actually getting the linear tendencies of the distorted flow, and not, for example, like aliasing or something, which is if our perturbations are in the nonlinear regime. Unfortunately, that gives us the nonlinear response. So we rule out those possibilities before we get out meaningful inferences.
Right. And is there a difference in terms of accuracy or the ease in extracting these frequencies from the superharmonics to the subharmonics? I can imagine that the superharmonics are fairly easy to pick up.
Easy to,
whereas the subharmonics are, the more sub they are, the more mingled they are with anything that projects too much onto a steady base flow and cannot be distinguished. So so we have a resolution limit towards the subharmonic.
Yeah. So I think that is more like the low frequency end of our spectrum. Like, how long do you need to integrate? But honestly, I think the most dominant, the most aggressive transition mechanisms that we see in the literature are around the ballpark of an integer multiple of, either it can be a subharmonic resonance or a fundamental resonance, or in the, so at least till now, we have only focused on the frequency limits as multiples of the fundamental. So, but we really need to push the technique to long time integration to see if it can actually capture like severely subharmonic components in the.
So I was especially worried about your multiple shock inlet. Because in that case, we already know that there are some really small, you call them the
bubble breathing
modes, right? And
so
many times the breathing modes are just beating modes of higher modes that are close together.
Different modes, basically.
So I was wondering, how that one plays into your interaction method.
So if you remember the original the original reference I cited with Tuber and Sendham, they did this body force linearization and did a long time integration of the signal, and they came up with something 2 orders of magnitude than the mean flow scale. So if you really, they came out from this implicit linearization, a scale which is 100 times, in time it's 100 times longer than the mean scale of the boundary layer U by delta. So there is proof that we can get low frequency unsteadiness, but if you really need to do that extreme long time integration to see if we can capture the bubble more. But that's why we have not done the bubble SBLI analysis. We are still with the ramp. Those we see that the ramp, we did capture the 0 frequency, the stationary mode. But that's not necessarily the breathing mode. That is just the curved wall. So, but when you come to the bubble itself, then there is this actual dynamics that happens at this low frequency.
It's almost a mean flow correction, right?
So we really need to test it. I cannot have very concrete guarantees on it, but I'm optimistic about it.
Good. All right.
They have already shown it in that paper. You can get some estimate of frequencies in it.
Good. Any other questions from the audience? I don't want to monopolize Uni here. Just unmute yourself. You don't need to raise the hand. Unmute yourself and fire away.
Yeah, I have a quick one. When you showed the hypersonic boundary layer, 2D one, and then you did the stability around time periodic basic
Yeah,
states.
yeah.
Do those time periodic states exist? Has somebody calculated them explicitly from the equations of motion?
Yeah, so there have been several DNS which has done the linear. They have done the non-linearly saturated periodic states. They have computationally they have shown that it exists, and even very well controlled experiments have shown that you get that rod-shaped structure when you have that periodic distortion in the mean flow.
Mm-hmm.
That's how I think in the late 1990s, experimentalists first found out that rod-shaped interwoven structure of macmode through shadow graph type visualization. I might not be correct, but through those that grayscale visualization, they could capture that rod-shaped structures. And that's how computations were first validated that, yes, we can capture that non-linearly saturated structure in the macmode by just simple harmonic forcing.
Mm-hmm. Mm-hmm. Okay.
And what happens is that the breakdown actually happens after that harmonic peaks. So it's quite well known that the breakdown doesn't happen where the primary mode is getting maximum amplification. It's far downstream. And the analysis shows that it's where that oblique mode really starts picking up and destroying the span-wise homogeneity. That's where you get this churning in the boundary layer, and that's when it really picks up. And that's why we need to do some sort of a secondary instability, either using operator-based or operator-free methods to have accurate predictions of where exactly it's going to break down.
Mm-hmm. But if you take say you take the equations and you just look for periodic solutions in time, mm-hmm. as you vary a parameter, and then you find this one with a certain frequency, can you then find another one where there's let's say a period doubling bifurcation that then could lead, I'm kind of thinking of a kind of a Feigenbaum cascade type situation.
So you could look at the perturbation equations and look at the first prime terms and then come up with that. But there has been some work on how to identify structures of superharmonics, but I'm not sure if there has been extensive work to do a real prediction of the distorted mean flow using purely theoretical means. I'm not aware of it myself.
Mm-hmm.
Yeah.
Good, thank you.
All right, any other questions? All right, well, people think about it. Let me squeeze another one in. In your UFP, is there any room for implementing control as you go along? Right now you're using that tool for analysis, prediction. For stability and prediction. But once you know what's in the flow and it comes out, could you actually, act on it almost immediately and apply some control?
Yeah. So the thing is that the UFP tool is now segregated from the actual DNS, right? So it's we are doing it separately. We are extracting the mean flow, extracting the harmonic, calculating the body force, doing it. But if we can sort of couple because it's the basic solver is the same. It's the presence or absence of the body force that's differentiating it. But if we can just do this in a
in that case, you want to embed it, right?
Yeah, embed it. We shouldn't wait till breakdown happens. The moment you have that superharmonic saturated and the the UFP picks up the span-wise peak, peak. If you can put some sort of actuation that dampens out the primary wave or maybe distort the mean flow itself, maybe we can push back that happening from wherever it is. And once that wave, because second mode is also very sensitive to mean flow scale. So if we can push back that wave a bit, it might not resonate with the critical layer and it might lose the translation mechanism.
Yeah. So and in this case, you could actually delay transition. Or do something, right?
Yeah, so we can just make it
similar. You mentioned that you saw Tamer Zaki's talk, right? So when he propagates these ensembles forward, you more or less do the same thing to figure out the stability of what happens, right? And in that case, you can also get enough information probably out to do some kind of a crude control
correction
that at least weakens it. May not eliminate it, but at least it weakens it.
Delay it, we can.
All right, good. More to do. All right. Any other questions for Uni? All right. Doesn't seem like it. All right. So thanks a lot, Uni, for a very interesting talk. Thanks for getting up early on the East Coast to give us.
No, that's fine.
And so we're gonna close it out. And thank you again for the presentation.
Thank you so much for this invite.
All right.
Thank you, Nate.
No problem.
Thank you.
Stay safe.
Yeah. Take care.
Bye.
Bye.